start the talk properly. So with the first question, it's one of those, me, the world, and whatnot. Why did I read the paper? So my motivation for reading this paper, and so I kind of, what are papers we love, and papers I like are those who make me think hard and create connections between places that I have never realized they were connected, and this is one of them. So why did I read the paper? It's a very simple question. So given an associative, can you guys see it? Okay. Given an associative operation star, the question that one would ask is how expensive it is to prove that two expressions are the same using just associativity. Right? I mean, of course, it's obvious to figure out that they're the same. You just remove all the brackets, and if there's the same string, then they're the same. Right? But that's not what I mean. I mean a proper, complete proof that will show you that these two things are the same, just using the rules of associativity. So, for example, let me have these two relations. A star B star C star D, it's equal with A star B star C times D. Right? So how expensive will it be to do it? Well, we actually need two steps. And, you could go longer than two steps, but two steps are enough, right? So you can distribute the CD towards AB, and then distribute the B into associate the B into this. So you need two steps. It can't be done in one. And the more complicated relations you have, the longer the story will be. Right? So I'm interested in things like theorem provers and things like that, and I'm also an algebraist, so associative operations are things that I like. So this is a nice, kind of simple problem that sounds reasonable, right, to pass. And of course, you all know that sort of brackets, expressions with brackets can be represented as binary trees. So in other words, here's the two pictures, the two trees, and they're of course too small, but anyway. So A times, these are stars here, right? So A star B times C is equal with A times, so this is the next move. And so the question is, what kind of operation is this? How did I go from from this to this? I mean, you can describe it in terms of just use associativity, or you can describe it as abstractly an operation on trees, right? And this is a problem that that I asked. But here's the second question: why did they write the paper? So they don't. Tarjan and Sleator are not algebraists; they are computer scientists. So what was their interest? And the question that they were looking at, this is in the late 80s. In mid 80s, they've invented this data structure called a splay tree, which is a self-balancing binary tree. So basically, when you throw in a new number in this binary search tree, you will go somewhere, and then you do this operation where you lift it back. Right? So basically, you try to rearrange the tree so that the new guy is at the top. It's the root. Right? And this operation is called splaying. So for example, these two trees are representing the same ordered structure, but they look quite differently. And so they were interested in this question: can I figure out how expensive this is in its most generality? I mean, surely you can write an algorithm and then check it and so on, but can I have a thought as to how much will it cost if I give you a tree that has 10,000 nodes? And you might, I mean, I'm sure you do. There's a lot of binary trees, right? I mean, once you pass 10, 20 nodes, you're not going to be able to use any computer to do with that, right? The Catalan numbers are the number of binary trees, and those grow quite quickly. So you can't just say, well, I'm just going to try it till the cows come home, because you won't. You have to be very clever with that. Okay, so this is an empty one. So questions so far? The two questions are kind of related, obviously. I mean, if you did realize they were the same tree. So here's the more general story. So suppose I have a binary tree like that. So I've got X and Y here. These are A, B, C are whatever kind of trees. So these operations that they were thinking about was to try to move X in the position of Y. So this is, I think they call it zig, and there's zigzag and zig-zig. I'm not going to talk about that. But the idea is to try to root this at X. And if you think about a binary search tree, what do you need? I mean, you need to do something about A, B, and C. And it's not too horrible to figure out that this is what's going to happen, right? So Y goes to the right of X, because in the search tree X is less than Y. And then, of course, B will have to go there, because this has to stay a binary tree, right? And so this is the operation that we're talking about. This is the rotation on a binary tree. Yeah? You look at this and you try at this node and you try to move it up. Yeah, and of course there's the same kind of thing here. It goes backwards. If you want to move Y there, then that's what's going to happen. Right? So for any node, if you want to move it to replace its parent, this is the operation of rotation. You just move it to the parent and rearrange the tree. And so the question that they were asking is, so again, you can interpret it in any of the two previous incarnations. The one that I was interested in, this is exactly applying associativity, and the one they're interested in, it's exactly trying to move a node which is down in the tree higher and higher towards the root. Right? So if you don't care about any of the two problems, just look at the problem. Look anew. This is where this starts. Take a binary tree. This is the operation. You move things up or down, or up. Sorry, not up and down. So the main question of the paper is the following: consider a graph in which the vertices are trees with n leaves, but with n leaves or n-1 internal leaves, whatever measure you have for the tree. And the question is, you're going to say that two vertices are adjacent if they can be obtained from one another by a rotation. Right, so this makes a very large graph. A graph as big as the number of binary trees with n nodes. And the question is, how far apart are the furthest apart trees? Right? Very simple-minded question. And it has half of an answer that's quite simple-minded. So the first half, as with anything, you'd like to know exactly what the diameter is, and we're going to get an upper bound and a lower bound. You will see quite soon that the upper bound, surprisingly, actually it was surprising to me that this is the case, right? You would expect that it'd be easy to find kind of lower bounds, right? And reasonable lower bound, because, why would this even be reasonable? Finding upper bounds for this, I thought it was hard, but it's not. In fact, the upper bound is easier, the lower bound is hard. And in fact, in the paper, the lower bound it's only obtained in some cases, as we will see. And there's, if you look at the MEET webpage, I posted a link to a recent article which actually solves the problem combinatorially. But I didn't like that paper because it's very clever. As with many clever combinatorial papers, you look at it and it's got a nice result, but then you're not any wiser for it. You've learned nothing but the fact that the author is very clever. Right? Well, in this, hopefully you learn some new stuff and connect some new stuff that you haven't before. So, the first clever idea is going from trees to polygons. And it's an idea that has been done before in various disguises. And this is perhaps the place where I'm going to spend a lot of time, because I want to figure out, I want to make sure that this is clear, because a lot of what follows is based on this idea. So you start with a rooted tree on n leaves, it will correspond to a triangulated polygon with n+1 edges. So, and then there are, both of them are qualified with rooted, so I know what the root is for both of them. And what is the root of a polygon is one of the edges, which I'm going to fix for all time. Right? So how do I do that? You start at the root, and every time you pick a new tree, a new vertex, you create another triangle. So let me actually draw a picture. So here's a very simple tree, ABC, and here's what happens. I'm going to start with A, and it's a binary tree, and it gives me this triangle. Right? And then B has a binary tree there, it gives me this triangle. And of course C gives me the yellow, the green one. Right? Now I'm going to glue these triangles together based on the relationships in the tree. So you see how it goes, right? I make a triangle each time with a vertex of the internal nodes, and I'm going to glue. You see, A is to the B is to the left of A, so I'm going to glue the edge that's opposite B to the left edge of A, and I'm going to glue the edge that's opposite to C to the right edge of A. Right? If one of the if the tree didn't have a left or a right edge, then I'm not gluing anything there. And so this is a gluing of triangles. So it gives you this 1, 2, 3, 4, 5 bone, right? And so let me draw it. The 5 bone looks like that. Yeah, so there's the central one and 2 triangles. Right? So this is a simple enough picture. Let me do the other picture. So this is another tree with 4 4 leaves and 3 internal nodes. And so what am I going to do? So kind of similarly, I start with B. B is now the root. And it's going to give me this edge. And there's nothing on the left, there's no internal node on the left of B. So I'm going to leave that B. A, it's going to give you the blue one, so it's connected to B because it's a right child of B. And of course C is a right child of A. Right? And of course this is again the 5 gone, but a different one. It's a different one. Yeah, it's a different one in some sense, right? All 5 gones are kind of similar, right? Up to rotations and whatnot. But from this point of view, it's a different one. And in fact, you can see very easily what the difference between this and this is. Perhaps it's not big enough to see, but so what? Anybody see what the difference is? So you see, the C seems to be kind of behaving similarly. But the difference between this is that this edge is like that, and the other one is the other one. So it's actually a flip of the diagonal, a flip of a diagonal. So basically, the rotations in the trees correspond to flipping diagonals in the sort of triangular representations of the polygon. Right. So there's the big picture. So you've got on the one hand side rooted binary trees with n internal nodes. Triangulations of a polygon with n+2 vertices and a distinguished edge. So what do I mean by triangulations of a polygon? I have a polygon with n+2 edges and a lot of triangles that make this polygon. So if you look at it, it's one of those problems, right, that you see on the web, right? How many triangles are in this picture? That's the kind of thing. There's all triangles. So the polygon is made out of triangles. There are no other shapes. There's no squares. There's no foregons or anything like that. It's made completely out of triangles. Right? And of course, there's a correspondence between this. You can go back and forth, right? It's hopefully clear that you can go back and forth. If I draw you the polygon, you can the polygon with this, and remember that this distinguished edge is the first opposition edge for the root, right? So I start from the root, and then I just walk through the polygon, through the triangles in the polygon. So, okay, corresponds to, okay, I have another picture, n internal nodes, one root, n minus 1 internal edges, n undistinguished exterior vertices, one distinguished edge, and n minus 1 diagonals. Right, so there's the correspondence, and rotation corresponding to an internal edge corresponds to the flipping with respect to the corresponding diagonal. So, if you never liked threes, forget about threes at this point. There's not going to be any more threes in the picture from now on. Right? So, I'm sort of working my way through sort of moving the story from trees. So now we're never going to talk about the left-hand side, we're only going to talk about the right-hand side. So now we don't have trees, we have a different question. We have a graph in which the vertices are polygons with a rooted edge and which are triangulated. Right? So there's a lot of those. And two such polygons are connected if one can be obtained from the other by switching one diagonal to another. So you take two triangles which are next to each other, they form a fourgon, which is split by a diagonal, you switch. This is one picture. You can see I've switched the red edge, the red diagonal to another, and now I'm going to switch the blue diagonal to that. Right? This is in fact the old picture. This is the picture of the three trees that I had in the first slide. So, turns out this is if you think this is an old picture, an old paper, it turns out that this question has been asked in the 50s with respect to some bizarre homotopy questions. So I'll get to that later. So it's a very old question, and which has recently received some new blood, if you like. So this is the question. So what is the diameter of this graph? Okay, I don't know. Perhaps you like trees more than this, but if you do, sorry. So here's a lemma. This is the one that I mentioned that is slightly easier. So if I have more than 12 edges to the polygon, the diameter of this graph is at most 2n minus 10, which is quite nice, right? It's a linear relation. You wouldn't expect that, right? Because it looks like there's so many trees or polygons. You wouldn't think that this diameter is so small, right? 2n minus 10 is nothing. So there's a linear, and in fact, it turns out this is the diameter. But we're getting ahead of ourselves. So it turns out that the theorem is that this lemma is not very hard to prove. I mean, it's, again, one of those combinatorial arguments that you're not going to be any wiser for knowing it. But it's kind of, here's a proof. Look at this polygon, right? So this one is okay. It's got 3 diagonals. We're going higher up. We're up and far. So it's a hexagon. So it's got 3 diagonals. So what I can do is I'm going to look at this and pick this vertex, and I'm going to try to move all the diagonals to move to this vertex. Right? So I'm going to switch as much as I can in order for all the diagonals to move to that vertex. If I did that, then I would have moved a random polygon to a polygon whose all diagonals start at one vertex. Yeah? So if I can estimate how long it takes me to do that, then twice as much would be how long it would be to go between 2 random polygons. Right? Because I would go to this is one of those, there's this concept of French railroad metric, right? Because if you take the train in France, it doesn't matter where you go from to in between any 2 places, you have to pass to Paris, right? So this metric is that, right? So in order to go from polygon A to polygon B, I'll always go to this polygon, which is this kind of conical one, right? But I'm looking for an estimate. I'm not saying that's the best I can do. I'm saying it's not going to be worse than that. So I'm allowed to do that. So I'm going to try to figure out how long does it take me from this polygon to the one that has all the edges here, all the diagonals here. Well, I mean, clearly, what do? I'm starting. So I'm starting by flipping the first one, and then I'm going to flip the next one. Right? So it took me 2 steps in this case. So let's try to figure out what I can do. So basically, I start with this polygon, and I'm moving to the left and right. So depending on how many diagonals I have coming out of it, I just have to move the others. Right? So this is the first trick here. So we need n minus 3 minus d moves to transform from this, where d is the degree of this polynomial, of this vertex, the number of things that come out of it. N minus 3 is because that's how many diagonals I'm going to have, right? And I have to throw away d because I don't need d, right? I already have d things coming out of it. So I just need to move all the others, right? So that's kind of, okay, I've got an estimate. So in other words, if I have 2 such polygons, for one of them the degree of this vertex is d1, and for the other is d, and for the other one is l, then the distance between the one which has degree d and the one which has degree l is no more than twice this, or the sum of those. So 2n minus 6 minus l plus d. Right? Okay, this part I kind of know. And I now need to look at d plus l. So how big could this be, d plus l, the number? So I take 2 random polynomials, just completely random, polygons, completely random, and I look at the same vertex in both of them. How much is the sum of these 2 degrees? Right? It's a question. I mean, it's a natural question. And so the point is that actually you start counting. You need to estimate d plus l. I'm going to start by estimating d, for example. Right? So how big could possibly d be? I mean, now, you know, I might have been. Can it be that d is always 1? I mean, can it be 2? I mean, I don't know. It's possible, right? I mean, if you have in the previous example I had, d was always 1, right? In the initial hexagon. So that wasn't very lucky, but I need to estimate in general. So what do? I'm looking at all the degrees of all the possible edges and adding them all together. Right? Okay. What happens? The degree of an edge is the number of vertex, is the number of edges that come out of it. If I'm adding all of them, I've got every edge twice. One to the left and one to the right. So the sum of all the degrees is twice the number of edges. Okay, but the number of edges, we know how to compute this. We've already did that. It's 2 times n minus 3, which is 2n minus 6. Okay, so that's a first computation, not a terribly hard one. There are n such vertices. So on average, the degree is 2 minus 6 over n. Average, right? I mean, could be that some are bigger, some are smaller, right? And if I add them up, right, the average of d plus l is 4 minus 12 over n. Right? So just probabilistically so, if I take a vertex, that's kind of what I expect the average to be. But of course, if n is very big, if n is bigger than 12, this is a bit bigger than 3. So it's got to be one that's 4. They can't all be, it's, you know, unless you're Michael Gove. You know that there will be things which are better than average, right? They can't be, all of them cannot be below average. So, so at least one of them will be 4 or more. So d plus l will be bigger than 4, which means that 2n minus 6 minus 4 is 2n minus 10. So a priori, this is it. This is the proof. I mean, okay, you have to make it a bit more formal if you want to be really nice about it, but that's that. I mean, actually, it's a much more detailed proof than in the paper. But again, it's a proof that tells me nothing. It's just a computation on this. It's clever, but that's it. So we've got this maximal distance, which is no more than 2n minus 10. Question is, could it possibly be that it's really tiny? Right? I mean, you would think that, right, so the same, in the case for the trees, it's 2n minus 6 if you have n internal nodes, because the number is this n plus 2 story, right? So, can it be, we have an upper bound, and as I said, surely this is the hard one, right? I mean, bounding it from above should be the hard one. What about from below? I mean, a lower bound should be easy because this is a hard problem, so presumably you know how to find very far away things, right? I mean, there's so many trees, you should be able to find 2 of them which are at distance n, right? So to convince you that this, well, okay, I'm not going to convince you, but I'll give you, if you get bored in 10 minutes, think about this problem. So here's a similar question that looks similarly hard, but is not. Suppose I give you a permutation of the numbers 1 to n, right? Just a random permutation. I've just rearranged it. And I'm asking you, look at this permutation, and I'm asking you, it's perhaps very far away, so it costs you a lot of time to get to it. So I'm allowing you to do the following thing. You're allowed to switch 2 things, or as many 2 things as you want. So a move consists as switching as many disjoint pairs as you want. So you send your minions to this faraway land and tell them switch to it, but they can't interact with each other. It takes them as much time to every pair of minions. So you can't just say, I switch 1 and 2 and 2 and 3. I can't do that. I can switch 1 and 2 and 3 and 4. That's fine. That's a move. So the question is, how many moves does it take to undo this? Right? Surely, yeah, so you mentioned switching and sending them. Right? How large is the diameter of this graph? A reasonably easy calculation, and with a little bit of sort of educated guess, if I take a cycle, 1 goes to 2, goes to 3, and so on, can be written as a product of n such transpositions, which are not, so you can do 1, 2, then 2, 3, and 3, 4, and so on. Right? So surely no cycle will be cost you more than n trips of your minions. Right? So an upper bound of n is almost immediate. Question is this a good bound? I mean, it looks reasonable. I mean, it will take you n moves to undo a permutation. And there's n factorial permutations, so perhaps that's a reasonable bound. The reality is very far from it. So is this bound tight? So it sounds like a similar kind of question. You make these moves, this graph, you walk in this graph. How expensive is it? The answer is 2. You can do it in 2 moves. So think about it. If you get bored, think about it. If not, you ask me again. So if you want extra hints, I'll give it. So sometimes problems which have an easy upper bound have this is really bad of an upper bound, and the lower bound is not n, right? So in this case, the question is not as hard as, well, it's harder, but it's not as far. So groundbreaking idea number 2, going from polygons to polyhedra, right? So it's going farther away from trees as you can see, right? So what happens is, and this is, again, this is where I'm going to stop drawing, because I can't draw in 3D to save my life. But you have to bear with me. So I'm going to start with 2 such objects, 2 polygons which are triangulated, and they have each they have an edge which is sort of marked. So what I'm going to do is I'm going to put them together, like if I'm making a samosa, or something, right? Or some sort of pie. Right? So basically, these are 2 polygons. Imagine them as pieces of paper, and you know where to start because they both have a marked edge. you glue that marked edge to itself, and then start gluing around. Right? That makes for some sort of object like that, which you can then imagine it has a hole, you blow in it, and it becomes a sphere. Right? That is a very standard little trick that topologists do. So here's my picture. So this was one polygon, the 5-gon, and the other one is behind. Right? It's going to look like that. It's very hard to imagine this, but if you think about like that, it's an easy mental exercise. It's just impossible to do anything with them, right? I mean, they exist. And another nice question about such problems is I've asked this from school kids, right? It's a very interesting question. If I have something like that, suppose you are on a planet whose shape you don't know. It might be a sphere, maybe it's a donut, maybe it's a two-hole donut. Can you do some computations with these triangles to figure out what the shape is? And in fact, you can. It's very famous, probably. But anyway, so I have this picture. Now I don't have polygons anymore, but I have these drawings on the sphere. Right? And now the idea, which is due to Thurston shortly, is that given a triangulation, you can make from it triangulations of the ball of the inside of the sphere, not with triangles anymore, but with tetrahedrons. Okay, they will be curved tetrahedrons, but they will be tetrahedrons nevertheless, right? So you basically think about the same. I mean, it's harder to imagine, but it's the same problem. Instead of having just triangles, you have a lot of tetrahedrons which share faces. Yeah? And they share a lot of faces, but at after you glue them together, you play some sort of game with them, right? They're like pieces of wood, right? And once you glue them together, they're going to have an exterior. The exterior is exactly the previous picture, right? So you think about all the possible ways. You take the previous picture, you chop off things that you don't care about, right, this is the sphere, and then you try to cut it into tetrahedron. Unfortunately, things are a lot harder in this case. Not only, I mean, in the case of a polygon, you have one invariant, which is the number of triangles you need. That's given, right? I mean, it's n-3. So, okay, fine, that's great. In this case, that's not the case. So you can make the same exterior from many kinds of many number of tetrahedrons. So basically, this is a union of deformed tetrahedron which shares some faces, and the conditions are that all the vertices of these tetrahedrons have to lie in this T, this exterior picture that I already have, and the faces, the exterior faces have to be in T. And as I said, this is a lot harder. The number of such tetrahedra is not an invariant of T. We have many combinations. Luckily, however, you can have, so you define T of T to be the smallest number of the best you can do. If you're making this into a puzzle for somebody, it's the easiest puzzle you can think of. It has the smallest number of pieces. And you call that T of T. And it just turns out that if P1 and P2 are two triangular polygons that you started with and you glue them together into this picture, this T of T is less than or possibly equal than the distance between the two. So I've got my lower bound. I've made this big picture. I've made this sphere. I cut it into pieces, and the best output I can get is a lower bound for my initial problem, right? This is, this clever idea. I don't want to prove that, but here's a next clever idea is, okay, how about that? How would I count this? I'm going to look at the biggest possible tetrahedra I can fit into the sphere, compute the volume of the big one, divide by the size of the biggest tetrahedra I can fit in the sphere, and that's a lower bound. right? Because this is made out of tetrahedron. The others are going to be smaller, so the number is going to be bigger. So sadly, this is not great because the fixed tetrahedron is the standard one, the regular one. It has a number size. The volume of the object that you have is going to be smaller than the volume of the sphere. So this is a lower bound, that is the volume of the sphere divided by the volume of the largest tetrahedron. That's just a number. It doesn't depend on n. So you've got the lower bound, but it's probably 3 or something, right? So it's not going to help you. I mean, I've actually wanted to compute this, but then I got distracted, so I don't know what the number is. It's a number. Anyway, it doesn't depend on n. So it's clever, but not that clever. But then the story continues because this is about Thurston. So, I mean, you might have heard about the first two, right, the computer scientists, but the third one is it's an extremely famous mathematician. He is perhaps the grandfather of low-dimensional topology. So he is the guy who actually created this whole area. So he really knew his way around these things. So he thought, well, why are we thinking about straight tetrahedrons and so on? Let's think about hyperbolic ones. So, you know, it's up to you how you measure such things. You might measure them as if you lived in a nice Euclidean space, or you can measure them differently. Now again, because I can't draw, I'm not going to talk about three-dimensional hyperbolic space, but I'm going to draw about a two-dimensional hyperbolic space. So, really, really clever idea, hyperbolic geometry. So I'm going to describe the two-dimensional one rather than three-dimensional one, because, well, I said I can't draw. So here's maybe a story rather than a complete description. So here's the picture you might have seen, right? It's not to gather. So it's a picture by Escher, and the point is that these things, this is, if you leave with anything from this talk, you should look at this picture and know that this thing is the same as this thing in area. That is the point of hyperbolic geometry. That the closer you are to the boundary, the smaller the things look in the Euclidean space, but their sizes are the same. So, from the point of view of hyperbolic area, this is the same as the old angels and demons picture where they're all the same. So, the big ones here look big, but the area of the small ones is in fact the same. So, there are two models of hyperbolic geometry. So, hyperbolic geometry came to us through, 2 centuries of people trying to figure out the parallel postulate of Euclid, right? So people tried for a long time to figure out. I mean, the parallel postulate says that if I give you a line in a plane, there's only, in a point outside of this line, there's only one parallel line to that. So they've tried to say, well, this is not right. It shouldn't be part of the axioms. We surely can prove that. And he went through 2,000 years of, well, maybe not 2,000, only 1,600 or something, right? I think, well, what was Euclid? Must be 500 BC or something. I said more than 2,000. So all of a sudden things came crashing down in the 19th century with probably first to figure this one out was Gauss, but Gauss was sort of a chicken, so he didn't publish anything about it. So 2 young mathematicians, a Russian one, Lobachevsky, and a Hungarian one, Bolyai, came to the same conclusion, which is that's got to be an axiom, otherwise you can construct different geometries. So there's a world in which if I give you a line, or whatever a line means, if I give you a line, there will be no line that passes through a point that's parallel to it, and there will be a world in which if I give you a line and a point outside, there will be infinitely many lines that pass through that, and the second one is what we're talking about. Yeah, so, after this was figured out, people started, there was a whole avalanche of things, and 2 models have been described. They tend to be associated to Poincaré, but they are not really due to Poincaré. They're much older than that. So the hyperbolic half plane. So think about a plane, cut it in half, look at the top half, and look at these pictures. These are lines in this world. So the lines in this world are either vertical or they are they're half circles whose vertex, whose center is on the horizontal line. The horizontal line, by the way, is missing from this picture. It's not there. So you really cut it. You can never get to that. Right? So lines are either this or this. So this is a triangle in hyperbolic geometry. Right? It's got three lines. But funnily enough, so is this. If I draw a third one, that would be a triangle as well. Although it's a little bit debatable whether you should call triangles with the vertices on the edge real triangles because they don't have vertices. But anyway. The point is, so the lines are verticals or half circles, and the distance is computed with a complicated formula that has to do with the logarithm of the. So basically, in order to compute the distance between 2 points, what you do is you draw the line between the 2 points. You look at these 4 points: this, 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 and this, and then you take some sort of cross ratio between these 4 points, and you take the logarithm of that. So essentially, what that means is that the closer if you go closer to this is kind of event horizon. You can never get to it. If you get closer to the horizontal line, then the measure becomes bigger and bigger and bigger. So you can't get to that. The second model is the one you saw in the previous picture. All right. So this example, this triangle is called an ideal triangle, the one that has the vertex in the ideal world. And it has, can you figure out, it's not too horrible to describe the idea of an angle in this world, right? What would be an angle between these two lines, right? They look really bizarre. So what the angle is you take tangents to these circles and you then measure the angle between these tangents. Of course, in my picture, the circles are both perpendicular to this line, so the tangents are the same. So this is a triangle whose all angles are 0. So it's a triangle which has 3 angles, all of which are 0. Yeah, so that doesn't happen very often in Euclidean world, right? There are no triangles with 0 angles, right? So the second picture is called the Poincaré disc. This is sometimes called, the previous one is sometimes called the Poincaré half plane. And it's kind of similar. The lines are either diameters of the circle or kind of little edges like that, which are perpendicular to the circle. So, and again, this is an ideal triangle. Again, you can compute angles the same way as you did before, and so on. So, what are some funny properties of hyperbolic geometry? 2 triangles are congruent if they have they have congruent angles. So you know this, your sort of the geometry from when you're a kid, right? Where you say 2 things are 2 triangles are similar if they have the same angles. This is better in this world. If they have the same angle, they're the same. Hence, what I was saying a bit earlier. The angel that's big, it's the same as the angel that's small because they have the same angles, right? They're just similar in the Euclidean world. Also, the area of a triangle is very easy to compute. It's pi minus the sum of the angles. So basically, you don't need to know anything about edges or anything. You just look at the angles, the sum of them. And pi minus, very hard to do that in Euclidean spaces. You always get 0, right? But in hyperbolic space, that's what it is. Right? So this is called, it's a version of a theorem that's called the Gauss-Bonnet theorem, which holds in more general world. Ideal triangles have the largest possible area. They have an area of pi. And of course, this is important. The area of a polygon, if I give you a polygon with n minus 2, with n edges, its area is n minus 2 pi minus the sum of interior angles. Right? Which is great because basically I can sort of make, I can have these polygons which have vertices on the boundary, so all the angles are 0, and therefore I'm going to have area to be n minus 2 pi, which depends on n, unlike the other ones, right? So there's no this, kind of remember the story, the clever idea number 2. There was a problem with the idea. You can divide by the largest tetrahedron, where the largest polygon will still have the volume, polyhedron will still have volume bounded by the volume of the sphere. Not so in this case. The volume of the sphere is infinite. So in this case, polygons have bigger and bigger volume, and so I have a chance to actually get to that. So those are some nice properties. The really cool idea is now think about the same story we had before with polyhedra, which are just tetrahedrons. But now the tetrahedron, you don't measure the volume in a Euclidean way, but in a hyperbolic way. That's the same story. Volumes are volumes. They still add up. So if I have 45 tetrahedrons in a polyhedra, 45, the sum of the volumes would be the volume of the polyhedra. So if I had a way of actually making bigger and bigger polyhedra and dividing by the size of the largest possible, there is still the largest possible tetrahedron included in a sphere. So that can be done, and in fact that's what they did, and this is the theorem which you're not going to see. So 2n minus 10 is less than this t of n for very large n of the type 10k squared minus 2 plus 2. It's a nice result. It tells you, there's a lot of numbers like that, but not all of them. And as I said, there's now proof that removes this from the picture, but and I think it's more than 12. But this is, what they did with this is amazing. They looked at some interesting polyhedra, for which they estimated the volume. There were really, really clever computations there, which I'm not going to talk about this. I'm going to run out of time. So, the graph from the set of binary tree with n inner vertices can be enriched to an n-dimensional object. So you can think about faces and bigger dimension things, which is called a CW complex, and its name, it has been called the associahedron because it comes from associativity. It's an interesting object. As I said, it's been discovered in the 50s by a guy named Sashev, which is this is not my quote. It's from somebody else, also from the 50s. His name I'm blanking out. So it seems to be very magical. It seems to have all kinds of funny properties. Some of the properties are not really the properties of isosahedron, but they're properties of as the next one I'm going to talk about, they're properties of the Catalan numbers. I don't know if you played around with Catalan numbers, but so Richard Stanley has a collection of uses of Catalan numbers. So there's 270 uses in his collection. So Catalan numbers, you just walk around and they're there. Right? They're basically ubiquitous. You count things, there'll be Catalan numbers. So here's my nice first application, power series. Oh dear, you can't see that, can you? Make it bigger now. So, oops, sorry. Maybe we can make it bigger this way. All right. Better. Right? So power series, these are just series. You might have seen this in calculus, right? A series of sum from I equal 1 to infinity of ci minus 1 xi and bi minus 1 xi. These are just formal things. You write them like that. You can compose them, right? The sort of function. You can compose them and ask yourself, okay, can I find two of them, f and g, so that when they compose, you get the identity? And as is the case with power series, what you do is you start looking at coefficients and compute relations on the coefficients. So, that's good. Okay, that's not what I want to do. What do I do if I don't want to do that? Okay. So these are relations on the coefficients. So B1 is minus C1, B2 is minus C2 plus 2C1 squared, and so on. These are things you can sit down and compute and you get them. Surprisingly enough, these coefficients can be read out of the isosahedron. So for example, for this one, if you look at the four-dimensional isosahedron. There's one three-dimensional one, 6 pentagons, 3 squares, 21 segments, and 14 points. And if you go further, these numbers fit. Again, this is related more to Catalan numbers than it is to the actual isosahedron, but it's still kind of cool. Right? These are two problems which are not related in any sense of the word. Right? There's two completely arbitrary algebraic objects. You combine them, and here's this combinatorial computation that comes out of some funny-looking picture. Right? The next one is the next two. I went once to a colloquium given by Isidore Singer, and he started by saying that a good talk should be, the first 5 minutes of a good talk should be understood by a landlord, and the last 5 minutes you shouldn't understand yourself. I'm getting to those last 5 minutes. So I understand these a little bit superficially. So there's some relation to homology and homotopy theory. So as I said, this is how these things have been invented. So the first construction is due to Stashev. And so what he wanted to construct is a way of actually reconstructing spaces or categories from their homology. So he discussed, this is his PhD thesis actually, and he did look at some things which are called H spaces, and they have been they're connected to the kind of abstract versions of topological groups, and they have nice sort of invariants, and he wanted to construct them back, and these isosahedrons had this property that you can look at the numbers associated with the isosahedron and go back to these objects. Again, this is obviously very big, and surprisingly, and so he defined these H spaces. These are generalizations of loop spaces, which in turn are generalizations of topological groups and so on. Surprisingly, these are some recent results in algebraic geometry and physics. So there's a theorem here, which is, I'm going to try to say what it means. So this is a theorem from maybe about 5 years ago, which says the following. The moduli space, it's a bizarre object in algebraic geometry. It's kind of a geometric object that parametrizes other geometric objects. In this case, what they parameterize is, if I give you a sphere, just a normal, the sphere that we were talking about, and I pick n points on this sphere, this is a geometric object. And they are different depending on how you put these points on the sphere. So if you try to classify all the possible way of putting these endpoints on the sphere, you get this geometric object called configuration of RP1. So this is a huge and complicated object, and then you mod out by invariants, by symmetries of this. And this is called the moduli space of the curves of genus 0 with n puncture. It's a very important thing for various things. So physicists like that for things that I know the names of, but I don't understand at all, so I'm not going to say. It has connections to a lot of algebra, a lot of Galois theory and things like that. It has connections to, obviously with topologies and things like that. So it's a very interesting thing that people have been thinking about for a very long time. And it turns out that these are objects that, for the last 150 years or so, the connection between mathematics and physics went pretty much one way, which is physicists needed some stuff, and mathematicians did that for them. That's not so much the case anymore. So there's a lot of results in this area which have been produced by physical intuition and then have gotten into mathematics. So there's some, actually there are things which have been computed in these accelerators. They compute cohomology of these kind of objects. So this is that's the kind of story. Surprisingly, this theorem tells you that you can make a compactification of this. So this is an object that has some open sides, so you want to close them down. So there's a standard compactification, and it turns out it's made out of these associahedrons. I mean, that is really weird, right? These are just combinatorial objects that classify these unbelievably big n-3 dimensional geometric structure. So there's n-1 factorial over 2 copies of these objects that just fit together. So there's a puzzle made out of these associahedrons that make up these unbelievably complicated things that have to do with things that happen in accelerators. So that's that. So I'll stop here. Questions? Maybe after a bit. Thank you.
Thank you.